up. Okay, so now we'll talk about equipotential surfaces. So we've defined the electric potential. So here's a diagram that shows you. So what this is showing you is on this surface, at every point, the voltage is electric potential is 9 volts. On this surface, everywhere it's 8 volts. And on this surface, everywhere it's 7 volts. So those are all equipotential surfaces. And what you learn now is that electric fields are perpendicular to the equipotential surface. So let's go. So let's say here's the surface that's an equipotential surface. So let's say everywhere on that surface, the electric potential is 10 volts. Okay. So now if you wanted to calculate the electric field at this point on the surface, the electric field is perpendicular to the surface. So there are two perpendicular to the surfaces, this one and this one. So which way is the electric field pointing? Well, it's perpendicular to the surface and it points in the direction of decreasing potential. So if this guy is 9 volts and this guy is 11 volts, so the electric field is not this one, but the electric field is this one. So the electric fields are perpendicular to equipotential surfaces and they point in the direction of decreasing potential. So for instance, if this was an equipotential surface, and this is 10 volts, 9 volts, at this point, the electric field is like that, and this point, the electric field is like that, okay? So, these are equipotential surfaces and electric fields are perpendicular to equipotential surfaces and point in the direction of decreasing potential. So here are two charges, positive charges, and the red lines are equipotential surfaces, and the electric fields are, you can see they're always perpendicular to equipotential surfaces. And so from the direction of the electric fields, you can surmise that this surface is at a lower potential than this surface, which is at a lower potential than this surface, and so on. So around the dipole, those are the equipotential surfaces, and the field lines are also shown. Okay, so since this is a negative charge, the electric field lines are pointing in this direction. So this is at a higher electric potential than this surface. Okay, and that's what's shown here. All right, now what we're going to show in the next couple of slides is the electric potential around a point charge. Okay, so here was the definition. If you wanted to calculate the electric potential at point B minus the electric potential at point A, all you have to do is this line integral from A to B, E dot ds. Okay, and you can do this line integral along any path, and that'll give you the same. You can do it along any path, and the value of the line integral will equal that. Okay, so the value of the line integral is path independent because this electric field was conservative. All right. So if you place a point charge there, and let's say you do the line integral for these 2 points A, B along this path. I'm not going to go through the details, but you can, so the electric field from a point charge is given by that, where r hat is a radial vector. So if that's the point charge, the r hat vector is always pointing radially outwards. Okay, so if you do this line integral, what you find is this. Okay, so this value. So VB minus VA equal to KQ, Q the charge of that particle. RB is this distance, okay? And RA is this distance, okay? So what you find is that, so what that implies is the electric potential from a point charge is KQ divided by R. So if the charge is positive, the electric potential is positive. And if the charge is negative, the electric potential is negative. So at a distance R from the point, the electric potential is given by KQ by R. So there, and electric potential is a scalar function. So it's a scalar quantity. And so this value is scalar. Okay, again, let's make sure we understand this. So okay, so here's a point charge Q. We want to calculate what is the potential at a distance R from this point charge. And what we found is K, the Coulomb's constant, divided times Q divided by R. Okay, so that's the electric potential at any given point R. Okay, so here is a plot of an electric potential. So let's say you confine yourself to 2 dimensions, to moving along 2 dimensions. So place the charge underneath that peak, and you can shown is the electric potential anywhere on that surface. Okay. So again, what's shown is this. So let's say you are on the XY plane. There's your charge. And if you want to find the electric potential there, the electric potential is that. And that's what's shown in that graph. Okay. So electric potential at all those points is equal to that height. Okay. So that's what's shown. This is the electric potential around the point charge. Again, there's the functional form. Now, if you had a bunch of charges and you wanted to calculate electric potential at various points, you just, so if you had these 4 charges, you wanted to calculate the electric potential at this point, you calculate the electric potential due to this guy, calculate the electric potential due to this guy, electric potential due to this guy, and just sum them up. Okay. And so around these 4 points, they've done this calculation, and they're showing you at all these points, the electric potential came up to 350 volts. So that's an equipotential surface. Okay. Dipoles, we love dipoles. So dipoles are 2 equal and opposite charges. Again, you all know what a dipole is. 2 equal and opposite charges separated by a distance. Okay. And the dipole is a vector. Okay. And it's Q times D. So the magnitude of the dipole is the charge divided by the distance. Okay. D is, so D is this vector. All right, so there is the dipole, and the electric potential around the dipole is shown like that. So the potential near a positive charge is positive, near a negative charge is negative. And what's shown here is this graph. See, so those potential curves, those are slices, horizontal slices of this graph. Okay. So these red circles or red curves are slices on the left, and these blue curves are slices on the right. Okay. Anyway, well, horizontal slices. So if you take a horizontal slice, you only get an intersection here on the left side. And if you take a horizontal slice here, you get an intersection on the right side. So the electric potential from a dipole, here's a dipole. And you can calculate the electric potential at that point. It's the electric potential due to this guy plus the electric potential due to this guy. And if you're far compared to this separation, you can show that the dipole potential is Kp cosine theta, where theta is that angle, divided by r squared. So the important thing to note is the following. The potential from a point charge falls off as 1 over r. The potential from a dipole falls off as 1 over r squared. Okay. Naturally occurring dipoles have very small charge separation. So we saw that the water molecule has a dipole moment. And what we're saying is in a water molecule, so here's a Mickey Mouse water molecule. Here's the negative charge and center of positive charge. What we're saying is so this is the oxygen atom, there's the hydrogen atom. This separation is very small. D in the dipole moment, Q times D. D is small for naturally occurring molecules. Yeah. The electric potential of a dipole at distances large compared to the separation falls off as the square of the distance. Okay. Now, if this was a thundercloud and you wanted to calculate the electric potential near the top of your house, what you would do is you would break this thundercloud into little pieces, treat that little piece as a point charge. There's the electric potential due to that point charge, and then sum over all those little pieces. And that's this triple integral that you would do. Okay. What this is showing you is the electric potential on a charged conductor. What it's showing you is the electric potential everywhere on the surface of a charged conductor is equal. Yeah. So the surface of a charged conductor is an equipotential surface. Okay, so here was the definition and change electric potential here. This was the general definition, which is equal to minus A to B, this line integral. But we saw from the previous chapter that all the charge resides on the surface of a conductor, and the electric field is perpendicular to the surface. So if you go along a path on the surface, E dot ds will come out to be 0 because here is the surface of a conductor. If the ds is like that and the electric field is like that, E dot ds is 0. Okay. So if you do the line integral along a path on the surface, okay, VB so the line integral along that path, A to B, E dot ds. And since this is 0, this is equal to 0. So implying VB equal to VA. The electric potential anywhere on the surface is equal to the electric potential at another point. So what this is saying is the electric potential is the surface of a conductor is an equipotential surface. And in fact, because the electric field inside is 0, it turns out that the entire solid is at the same electric potential. Okay. So the surface of a charged conductor is an equipotential surface. And since the electric field inside is 0, V is constant inside the surface and is equal to the value on the surface. So if you take a solid, if you take a conductor and put charge on it, all the charge resides on the surface. So, so now between last chapter and this chapter, here's what we can say. So for a conductor, okay, here's a conductor, so a piece of copper or something like that. If you go to a store and buy some charge, and throw it on the conductor, the charge will reside on the surface. So that's one thing we can say. The second thing we can say is E equal to 0 inside the conductor. And now from this chapter, what we can say is V is constant everywhere on the conductor. Okay. So we learned 3 things now about charges on conductors. Yeah. So that's what this is showing you. There's a spherical conductor with some excess charge. The potential outside the conductor is as if it was a point charge. And the electric potential is constant everywhere on the surface and constant and has the same value everywhere inside. This is showing you the electric field. The electric field is that of a point charge, and the electric field is 0 inside. Okay, so what this is showing you is the following. So let's say you have a region where the electric field is constant. Okay, so there's this electric field. And what we're going to do is, now we're going to take this solid and a conducting solid and bring it into this constant electric field. And here's what happens. So prior, the electric field was constant. When you brought in that conducting solid, since the electric field inside the solid has to be 0, the charges on the conductor redistribute such that, and the field in the surrounding changes like so. Okay, so you went from a constant electric field like that to the field change because you brought in the conductor. Okay. And so the electric field redistributed like so. Okay, so that's what we talked about Faraday's cage. We talked about Faraday's cage in the last chapter. And here's a picture of the Faraday's cage. What the Faraday's cage does is it's a metal cage. And what it does, it shields you from any external field. So there's an external field, and the cage shielded you from the external field. Inside the cage, the field, electric field is 0. Okay. So how does this work? We saw this last time, but again, we'll do it again. So, so here's an external field. Okay. And if you turn on this external field in a Faraday's cage, a metal cage, what happens is the free charges in the metal respond to this electric field instantly. And what they do is, so negative charges would collect here. So almost instantly, that will induce an electric field in this direction. Okay, so that's the induced electric field. This was the external electric field. Yeah. And so the net field inside is external plus induced, and that's 0. Okay, so the net effect is, so the net effect is if you had a Faraday's cage and you turn on an external field, that field will not penetrate the insides of this Faraday's cage. Okay, and that's what's shown here. Okay, so hence during a thunderstorm, when electric fields are strong near thunderclouds, one of the safest places inside a metal cage, your car, for instance. Okay. All right, we will pause now because now we're going to